Student, Assalamu alaikum wa rahmatullahi wa barakatuhu. In this video, I shall explain the reason for why the energy of T2g is lower in octahedral complex while higher in tetrahedral complex. First, remember the D subshell pre-metal ion consists of 5 orbitals dxy, dzx, dyz, dx square minus y square and dz square. All these orbitals are degenerate, that is have same energy, but when ligand come toward pre-metal ion, it splits into various groups. The first group is EG group. EG means doubly degenerate group, a group of two orbitals which have same energy. It consists of dx square minus y square and dz square. EG sets have lobes along bond direction and can participate in bonding. These are called bonding orbital because its lobes are present along x-axis. This is x-axis, this is y-axis. The lobes of these orbital are present on x-axis and y-axis. The second is dz square, whose lobes are present on z-axis. Now the second group consists of T2g subset, triply degenerate group of orbital. G means whenever G comes with T2 or with T, then we talking about octahedral complex. In case of tetrahedral, we write only simple T, simple capital T. This is the main difference between tetrahedral complex and octahedral complex. T2g subset consists of 3 orbitals dxy, dyz and dzx. These are called non-axial orbital. Non-axial orbital means those orbitals whose lobes are present between x-axis. This is x-axis, this is y-axis, and this black structure represent one lobe of orbital. So its lobes are present between x-axis, that is why it can't participate in bonding. Now, how ligand field theory explains the tetrahedral complex. In tetrahedral complex, 4 ligands attached to central metal atom. The d orbital also splits into 2 different energy levels. This is the 5 degenerate orbitals. The top consists of 3 T2g orbitals and the lower consists of EG orbital. Why the energy of EG is higher while that of T2g is EG is lower and that of T2g is higher in case of tetrahedral complex. Remember, the energy of those orbitals will be high, which is in directly contact with ligands. And also remember, ligand approach along x-axis, but here the lobe of T2g is present between x-axis. how they can participate in bonding. Now consider a cube-like structure. This is a cube-like structure. In center we put metal ion. This is y-axis and x-axis. This is the orbital of dxy or dyz or dzx, whose lobes are present between x-axis. Remember, this lobe direct toward corner. This is the corner. And the ligand approach in case of tetrahederal complex along the corner, not along the x-axis. So the two orbitals, that is the two orbitals of Eg, whose lobe on x-axis is present on this pink line and this orange line. So here is no ligand. When there is no ligand, there will be no inter-electronic repulsion, and the energy of this orbital will be lower than t2g. This triangle indicates ligands. The yellow triangle indicates ligand, and it approach or come along the corner. That's why T2G energy is higher and Eg is lower. In octahedral complex, 6 ligands attached to central transition metal atom. The energy of Eg is higher than T2G because the lobe of Eg orbital is present along x-axis and ligand approach along x-axis in octahedral complex. Due to inter-electronic repulsion, the energy of Eg is higher than T2G. In square planar complex, the orbital of d subshell splits into 4 groups. The energy of dx square minus y square is higher than dxy, then dz square and dzx and dyz. Why? Because ligand approach or come along x-axis and y-axis. This is x-axis, this is y-axis, this is metal ion. The red sphere indicate ligands, and this come toward metal ion along x-axis and y-axis. Due to inter-electronic repulsion along x-axis and y-axis is maximum, and dx square minus y square, then dxy, then dz square, then dzx and dyz. In z-axis there is no ligand, so no inter-electronic repulsion. That's why the energy of dz square is lower. The energy of dxy orbital component is high because ligand comes along x-axis and y-axis. Please subscribe my channel.